Myself Nikita Mishra from Department of Chemistry, Gujarat University. I welcome you all in the refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor Director UGC HRDC, and Dr. Dilip Wasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, Gujarat University. Session is Dr. Chetan K. Modi, Associate Professor, Applied Chemistry Department, Faculty of Technology and Engineering, the Maharaja Sayaji Rao University of Baroda. He has total 18 years of academic and research experience, including UG and PG. His broad area of research includes graphene-supported heterogeneous catalyst, glowing photoluminescence carbon quantum dots with diversified possible applications, host-guest chemistry of zeolite by entrapped nanohybrid materials, metal nanoparticles decorated on solid support at heterogeneous catalyst, supported ionic liquids on porous inorganic materials. Total 3 PhDs awarded under his guidance and presently 5 are working. He has around 20 MSc dissertation projects. He has 32 international, 2 national research publications with 2 book chapters published in international publications. Moreover, he has completed 1 research project funded by UGC New Delhi. 1 project is ongoing from UGC DAE CSR Indore. He has presented more than 40 papers in seminars, symposiums, workshops, and conferences of international, national, and state level. He has received Certificate of Appreciation from the Faculty of Technology and Engineering, MS University of Baroda, for publishing research article with cumulative impact factor of 11.68 in the year 2018. He has received Certificate of Outstanding Reviewing Award from various international journals such as Applied Organometallic Chemistry, Bile in 2018, Catalysis Communication Journal, Elsevier in 2016, and many more. Moreover, he has worked as Associate Editor as International Journal of Chemical Research. Also, he is having a life membership of Indian Chemical Society ICS Kolkata and life member of Society for Material Chemistry SMC Bagh, Mumbai. He is serving as member of Board of Studies in Applied Chemistry and member of Faculty Board of Technology and Engineering MS University of Baroda. He has served as co-opted member of Board of Studies in Chemistry HNG University Patan during tenure of 2012 to 2015. Also a member of Board of Studies in Chemistry MK Bhavnagar University during 2011 to 2014. Also worked as a resource person in the UGC sponsored refresher course in chemistry at Gujarat University Ahmedabad and at Amravati University. Delivered as expert lectures in skill development workshop on polymer in automobile applications under the COEP MS University of Baroda. He has delivered lectures under UGC Visiting Fellowship Program at SP University, Vallabh Vidyanagar, Gujarat, and invited talks at various national, international conferences, seminars, and symposia. He is a reviewer for recommending the manuscript for publications in various reputed international journals. Thank you.
I, Dr. C.K. Modi, would like to thank the UGC, HRDC, that is Human Resource Development Center of Gujarat University, for allowing me to connect with you and deliver my session on the topic Symmetry and Group Theory in Chemistry. I would also like to thank especially 2 people, Dr. Jagdish Joshi, Professor and Director of UGC HRDC, and Course Coordinator, Dr. Dilip Wasawa, Department of Chemistry, Gujarat University, to make every possible effort in all the activities and programs about UGC HRDC. And I can assure you that they have been completed successfully. So now look at the title of my presentation, that is Symmetry and Group Theory in Chemistry. Now, what do you mean by symmetry? Now, symmetry means the same. Now the term symmetry means, what do you mean by symmetry? It means a structure in which all the parts which are in harmony with each other, as well as to the whole structure. So we can say that the more it changes, the more it stays the same. That is called symmetry. Now, while we are talking about the nature, there are countless examples they are of having symmetry, like flowers, leaves, animals, etc. So they are all symmetrical. Now, few more example. Now, look at this example, like butterfly. Now, butterfly, which is symmetrical. So how can we say that it is symmetrical? Look at this. So if we draw a line passing down the center of that butterfly, which divides into two parts. Now, both these parts, they are mirror images of each other. So this part, which is mirror images of this part, and therefore it is symmetrical. Look at this human faces. Now, if a line passing through the center of this face, which divides into two parts, now this part, which is a mirror image of this part, and therefore we can say that it is symmetrical. Look at this insect, which is also symmetrical. Okay, this part is mirror images of this part. Apple. Okay, so all these examples, they are symmetrical. Now, on the other hand, now look at this image of this tree, where you can pass the line passing through the center of this tree. However, this part is not mirror images of this part. Therefore, it is asymmetric. So all these lines, they are vertical line. Same way, horizontal line. Now look at this scissor. If we can pass horizontal line through the center of that scissor or bow and arrow, or look at this example, ladybug. So if we can pass a horizontal line passing through the center of this molecule or compound, where it divides into two parts, both the parts which are mirror images of each other. So this is called side to side. Now, in some of the objects where both vertical line as well as horizontal symmetry, both are present, like CD. Look at this. This is a vertical line passing through the center of the CD. Okay. Same way, if we can pass horizontal line. Okay. So here, vertical symmetry and horizontal symmetry, both are present. Now, symmetry, while we are talking about the symmetry, it has a number of elements or operators or operations. Okay. So what do you mean by symmetry elements? Now, symmetry elements are nothing but the imaginary geometric entities. So they are imaginary geometric entities. So these entities might be points, it may be lines, or it may be planes. Okay. So when a symmetry operations are performed around the molecule, okay, so it gives an indistinguishable configurations. So suppose if we are performing any operations on the molecule, so after performing such operations, we are getting the indistinguishable structure. So then we can say that the molecule have a symmetry. So all symmetry elements leave the molecule in an equivalent positions. Okay. So all of you just keep in mind that while performing any operations on that particular molecule, okay, so which leaves the molecule in an equivalent positions, or equivalent positions, or we can say that indistinguishable positions. So before and after the operations, both the structures, original structure, and after performing that operations, we are getting the new structure. Now both the structures, they are equivalent. Look at this. Now suppose if I perform symmetry operations on hydrogen molecule. Now hydrogen, which is a linear molecule, now there are two hydrogen, H and H prime. Look at this. Okay. Now, if I can pass imaginary line passing through the center of that molecule. Now, this line, if I can rotate it around certain degree of rotations. So after certain degree of rotations, if this H prime, this H changes to H prime, or H prime changes to H. Okay. So after performing these cyclic operations, what will happen on z-axis at around 180-degree rotations? This H comes over here and H prime comes over here. So look at this, the another structure. After performing cyclic operations on this imaginary axis at around 180-degree rotations, and we are getting the equivalent structure. Okay, so this is z-axis. Okay, look at this ball and stick. These are the two hydrogen. If we assume that these are the two hydrogens, and this imaginary line, if I can rotate this imaginary line at around 180-degree rotations, after 180-degree rotations, this H comes over here and this H prime comes over here. Okay. Now both these structures, they are equivalent structure or indistinguishable structure, right? The positions of H prime and H will remain as it is. Okay, here. Now symmetry elements. Symmetry elements, there are 5 important symmetry elements. Which one? That is, first one is called identity. So identity E. Second symmetry elements, which is called as axis of rotations, or which is also referred as rotation axis, which is symbolized by Cn. Third operations or third symmetry elements, that is called mirror plane, that is symbolized by sigma. Fourth symmetry elements, that is called center of symmetry, or which is also referred as inversion center, which is symbolized by I. And the fifth symmetry elements, that is called improper rotations, or it is called as rotation reflection axis, which is symbolized by Sn. So these are the 5 important symmetry elements. So why we are when we are talking about the symmetry, so it would have 5 symmetry elements: identity, that is symbolized by E; axis of rotations or rotation axis, which is symbolized by C; and third one, that is called mirror plane, which is symbolized by sigma; fourth one, that is called center of symmetry or inversion center, which is symbolized by I; and fifth one, that is called improper rotations or rotation reflection axis, which is symbolized by Sn. Now we shall discuss one by one. Look at this, the first symmetry element, that is called identity. Now identity means no change is made in the molecule after performing identity operations. So when we are talking about identity, okay, so suppose if we are talking about any particular molecule, and if we perform identity operations, so after performing identity operations, what we are getting? We are getting no change in that molecule. Okay, so that means all operations, operations which brings back the molecules to its original positions, right? So when we are performing any identity operations to the molecule, no change is made in the molecule. The molecule will remain as it is. That is called identity. Okay, so every molecule, compound, structures, okay, living or non-living molecules or entities, they are all having identity. Okay, so we are all having an individual identity. So identity is always present in any particular molecules or compound. Second, that is called center of symmetry, I. So which is symbolized by I. Now, what do we mean by center of symmetry? Now look at this definition, simple. An imaginary point in the center of that molecule through which the reflection of each atom can be performed. Okay. So for example, this is dimethyl mercury. Now in dimethyl mercury, this is the center of that molecule. Okay. So if we consider the center, right? Now, if I can start my journey from this atom, A atom, okay, so the center of that molecule, this is the center of that molecule. Now, on the other side of a center, at the same distance, if I can find the same atom, okay, if I can find the same atom, then the molecule have center of symmetry. Okay. Same way, the another example, chromium hexacarbonyl, right? Now look at the my cursor. If I can start my journey from this point, okay, this is the center of that molecule. If I can start my journey through the center, okay, this is the midway. Now on the other side of a center, at the same distance, if I can found the same atom, then the molecule have center of symmetry. Look at this. If I can start my journey from this point through the center of that molecule, this is the center. On the other side of a center, at the same distance, if I can found the same atom, then the molecule have center of symmetry. Okay. So these are the molecules where the center of symmetry I is present. Okay. So I is nothing but imaginary point, which is situated within the molecule at the center, and through which the reflection of each atom can be performed. Okay. इसका reflection यहाँ पे मिलेगा, इसका reflection यहाँ पे मिलेगा. So if I can start my journey from this point through the center, on the other side of the center at the same distance, if I can found the same atom, then the molecule have center of symmetry. Okay. Now the third one, the third symmetry element, that is called axis of symmetry or rotation axis, which is symbolized by Cn. Now this axis of symmetry or rotation axis, this is an imaginary axis. Look at this image, where this imaginary axis passing through the center of that molecule. So it passing through the molecule around which the rotation can be performed. So if I can perform the rotation of that imaginary axis at around a particular degree of rotations, so after a particular degree of rotations, if I can get the equivalent structure after performing these cyclic operations. Okay. So for example, if I can perform these cyclic operations on this rotation axis at around 120 degree rotations. So 120 degree rotations, what will happen? This atom comes over here, these atoms comes over here, and these atoms comes over here. Okay. And the new structure, this is called equivalent structure, right? So after performing cyclic operations, इसको हम cyclic rotate करेंगे at around 120 degree. So after 120 degree rotations, these atoms comes over here and these atoms comes over here, as well as these atoms comes over here. Okay. So for n 2 pi by n rotations, there is an n-fold axis of symmetry. So which is symbolized by Cn. Now pi stands for the total degree of freedom 360. Okay. So if I can perform 120 degree rotations, 120 degree rotations, so 360 divided by 120, what is my answer? So 360 divided by 120, the answer is equal to 3. So this rotation axis, which is symbolized by C3. So n, that is called number of fold. Number of 4. So कितनी डिग्री पर हमने रोटेट किया, that is the important thing. Okay. Now the two-fold axis of rotations. Look at this. Why it is called C2? Okay. So why this imaginary axis is called C2? Now this is an example of water molecule. This is oxygen, which is situated at the center, and these are the two hydrogen. Now, if we can pass an imaginary line passing through the center of that molecule, and if I can perform the cyclic operations of that imaginary axis at around 180 degree rotations, अब इसको हम 180 degree पे rotate करेंगे, so what will happen? This hydrogen comes over here and this hydrogen comes over here. So after 180 degree rotations, we are getting the new structure. Now look at this structure. Now this structure and this structure, what is the difference? The difference is nothing. Okay, only the positions of H3 and H2, they have interchanged their positions, right? But the structure is equivalent. So both these structures are equivalent, but this is not identical structure. उसको हम identical structure नहीं कह सकते because H3 and H2 they interchange their positions, but they are almost look like same structure, and therefore we can say that equivalent structure. So this operation is called cyclic operations, or this is called axis of rotations. So if water, there is an C2 axis, we can perform a two-fold 180-degree rotations to get the identical arrangement of the atoms. So this is called two-fold axis of rotation. Same way, three-fold axis of rotations. Like if we are talking about the trigonal planar structure, like BF3, BCl3, okay. So in that case, for example, BF3. So boron, which is situated at the center, and the three fluorine atoms, they are at the edge sides. Now, after performing a cyclic operations, so if we can pass an imaginary line, passing through the center, यहाँ से pass होगी, and if we can perform a cyclic rotations, so after cyclic rotations, what will happen? This F comes over here, this F comes over here, and this F comes over here. Okay, so look at this new structure. So after 120-degree rotation on Z axis, what will happen? We are getting the new structure, right? Where all these three fluorine atoms interchange their positions. However, boron, which is situated at the center, because the imaginary axis passing through this boron atom. So the position of boron will remain as it is. Again, on the same axis, if we can perform, look at this axis. If we can perform another operations, so after 120-degree rotations, this fluorine comes over here, this fluorine comes over here, and this fluorine comes over here. And we are getting the equivalent structure. So all these structures are equivalent. So therefore, this molecule have axis of rotations which is situated on the Z-axis. So BCl3, look at this structure, three-dimensional structure, where if we can pass then imaginary line in such a way that now if we can rotate this imaginary axis, so all these three atoms interchange their positions. Or look at this structure, if we can pass this line, if we can pass this line to the centers, and so that now if I can rotate this imaginary axis so that these three atoms interchange their positions. So rotation axis. The rotation axis is where there are a number of rotation axes. So it depends upon the number of fold value. So n stands for number of fold. So n is equal to 2. So if we perform cyclic operations, 180-degree rotations, then the value of n is equal to 2. Because 360 divided by 180, what is the value of n? So n is equal to 2. If we perform 120-degree rotations, for example, look at this imaginary axis passing through the center, and if I can rotate this imaginary axis at around 120-degree rotations. So after 120-degree rotations, what will happen? These atoms comes over here, these atoms comes over here, and these atoms comes over. But if I can perform 180-degree rotations, we are not getting the equivalent structure. So all of you just keep in mind that only after the performing of 120-degree rotations, these if I consider as an NH3 molecule, this is a nitrogen, and these yellow circles which indicates that hydrogens. So these are the three hydrogens. And if I can perform 120-degree rotations, all these three hydrogens interchange their positions. So this is called equivalent structure. That is called 120-degree rotations. Therefore, 360 divided by 120, the value is equal to n is equal to 3. So this rotation axis is called C3. Same way, if I can perform 90-degree rotations, the square planar molecule. So in a square planar molecule, where the molecule, if I can perform 19-degree rotations, so after 90-degree rotations, we are getting the equivalent structure. I will show you later on. Okay. Same way, benzene structure. If we are talking about the benzene structure, so in benzene structure, all the corners, they are occupied by the carbon atoms. Okay. So the 6 corners occupied by the carbon atoms. Now, from the center of that benzene molecule, if we can pass the imaginary axis, and if we can rotate at around 60 degree. So after 60 degree rotations on the z-axis, what will happen? All the 6 carbon interchange their positions. And hence, we can say that the benzene has C6 rotation axis is present. Sometimes infinite rotation is also present. I will show you later on. Okay. When we are talking about the linear molecule always have C infinite. Okay. Now, sometimes the molecule have not only one rotation axis are present. It may be probable that the molecule have more than one rotation axis are present. Okay. So, look at this example, the square planar molecule. Now, this is the square planar structure. Now, in this square planar structure, there are a number of rotation axes are present. So, look at this. The one axis which is passing through the center of that square planar, and if I can rotate at around if I can rotate at around 90 degree. So after 90 degree, what will happen? This structure where the all corners occupied by the, for example, यहाँ पे one hydrogen, second hydrogen, third hydrogen, 4 hydrogen. So all these 4 hydrogen interchange their positions, right? So therefore it is called C4. Same way, it has a number of C2s are also present. Okay. There are 4 C2s are also present. So in this square planar molecule, not only one C4 is there, but it would have 4 C2 axes. These are called subsidiary axes. Okay. Now, principal axis. So among these 5 axes, rotation axis, which one is considered to be a principal axis? Now, those which have highest order. So among these 5 rotation axes, these are the C2. This is C2. This is C2. Now, this is C4. So the n value is higher. Therefore, it is considered to be a principal axis. Now, in benzene molecule, previously I was discussing about the benzene molecule. If we can pass the imaginary line passing through the center, and if I can rotate at 60 degree, so after 60 degree, so 1, 2, 3, 4, 5, 6, all these 6 carbon, they interchange their positions. Therefore, it is called C6. Okay. Along with number of C2s are also present. So if I can pass this axis, look at this axis dotted line, and if I can rotate this axis at 180 degree rotations, so what will happen? 4 carbon interchange with 6 carbon, 3 carbon interchange with 1 carbon. Okay. However, 5th and 2 carbon, they are remain as it is because they are situated in between the axis. Same way, if I can pass this imaginary line passing through the center, and if I can rotate this imaginary line so that 3 carbon interchange with 4 carbon, 2 carbon interchange with 5 carbon, and 1 carbon interchange with 6 carbon. So this is C2. So after 180 degree rotations, we are getting the indistinguishable structure. Same way, the third one. Same way, this is fourth one, right? This is fifth one. Sorry. This is fifth one, and this is sixth one. So how many C2s are there? 6 C2s and 1 C6 axis. So which one is considered to be a principal axis? Highest fold order rotation axis, that is C6, is considered to be a principal axis. Now next one, that is called mirror plane. Now mirror plane, another symmetry elements. What do you mean by mirror plane? Now mirror plane is nothing but an imaginary plane within the molecule which divides it into the 2 parts, and both the parts which are mirror images of each other. So if we can pass an imaginary plane passing through the center of that molecule or object, it divides into 2 parts. Look at this. Human body, if we can pass mirror image through the center of that human body, it divides into 2 parts, this part and this part, both this part which are mirror images of each other. Therefore, it has mirror plane. Now look at this linear molecule. like pencil. Now pencil having not only one mirror plane, it has an infinite number of plane. यहाँ से भी हम पास कर सकते हैं, यहाँ से भी पास कर सकते हैं. So, if we can pass the mirror plane, यहाँ से पास कर सकते हैं, यहाँ से पास कर सकते हैं, यहाँ से पास कर सकते हैं, and we are getting the mirror image through this mirror plane. Therefore, linear molecules have infinite number of planes. So all of you just keep in mind that while we are talking about the linear molecule, any particular linear molecules, they are of having infinite number of mirror plane. Now, mirror plane, there are three types. Actually, there are three types of mirror plane. Which one? So it would be classified into three categories: sigma V, sigma H, and sigma V. Now, what do you mean by sigma V? Sigma V plane, that is called vertical mirror plane. V stands for vertical. Now, what are the conditions of this vertical plane? The plane which is parallel to the principal axis. The plane which is parallel to the principal axis and also passing through the center of that molecule, and it divides into two parts. And both the parts which are mirror images of each other. So there's the conditions for sigma V. Same way sigma H, horizontal plane. Now what is the condition of a sigma H? The plane passing through the center of that molecule and it divides into two parts, both the parts which are mirror images of each other. And second condition is plane which is perpendicular to the principal axis or rotation axis. Okay, so those plane which is passing through the center of that molecule and divides into two parts, along with if it is perpendicular to the principal and the rotation axis, that plane is called horizontal plane. Sigma D, the third plane, the plane passing through the center of that molecule and it divides into two parts, both the parts which are mirror images of each other, as well as the second conditions, the plane parallel to the principal axis and passing through the angle between the two subsidiary axes. I will show you later on. So it will passing through the angle between two subsidiary axes. That is called sigma V. Now look at this one by one. We can say that sigma V. Now this is a water molecule. This is oxygen and these are the two hydrogen. Now if we can pass this plane, it divides into two parts, both the parts which are mirror images of each other, as well as it is parallel. Look at this C2, this line which reflects C2 axis. So which is parallel to the rotation axis or principal axis. So यहाँ पे क्या होगा? The plane passing through the center of that molecule and it divides into two parts, and both the parts which are mirror images of each other, as well as it is parallel to the rotation axis. Therefore, this is called sigma V. Okay. Another plane. Look at this. Now, this water molecule, if we can pass the second plane in such a way that these atoms, they cut in a halfway on the front side and on the back side. So it divides the molecule into two parts, and both the parts which are mirror images of each other and which is parallel to the rotation axis. So this plane is also called as sigma V. So water molecule has how many sigma V planes are present? So water molecules have two sigma V, 1 and 2. So both this plane, it passing through the molecule and divides into two parts, both the parts which are mirror images of each other, and it is parallel to the rotation axis. Look at this. यहाँ से आपको clear दिखाएगा. It is visible. Look at this one plane. This is called sigma V passing through the center. ये जो है, this is passing through the center of that molecule and divides into two parts, both the parts which are mirror images to each other, and it is also parallel to the rotation axis. Now second plane, the pink plane, look at this, it passing through the molecule and cuts the molecule or atoms in such a way that half part of this atom mirror images of the remaining part which is on the back side of that atom. Same way, this atom on the front side and the back side. So it cut the molecule into two parts, both the parts which are mirror images of each other, as well as it is parallel to the rotation axis. So in water molecule, this is water molecule has how many sigma V planes are present? Two sigma V, 1 and 2 sigma V. Now, in water molecule, is there any sigma H molecule is there? Sigma V, sigma H is present. So what is the condition of sigma H? Horizontal plane. So it passing through the center of that molecule and divides into two parts. Okay. It divides into two parts. So if we can pass, and the second conditions for the mirror plane is it is perpendicular to the rotation axis. So perpendicular kab hoga? If we can pass this mirror plane and in such a way that it is perpendicular to the rotation axis. But यहाँ पे sigma H is absent because we are not getting the mirror image. Okay, if we can put the plane in such a way that we are getting the mirror image, but it would not be possible for us here, and therefore we are not getting the mirror image. Therefore, sigma H is absent. A horizontal plane. Look at this. Look at this molecule. This is trigonal bipyramidal structure. Now this trigonal bipyramidal structure, if we can pass this plane in such a way that it divides the molecule into two parts, both the parts which are mirror images of each other. Okay. And this is the rotation axis, C3 axis or principal axis, which is passing through the center of that molecule and which is perpendicular to this plane. Therefore, this plane is called horizontal plane. Look at this square planar molecule. Now, in this square planar molecule, this plane, what it reflects? It reflects this is sigma H plane. So this plane passing through the center of that molecule and it divides into two parts, as well as it is perpendicular to the principal axis. Therefore, this plane is called horizontal plane. Now, dihedral plane. Now, what are the conditions of dihedral plane? Look at this. Now, the conditions of dihedral plane is, so these are the two dihedral plane. Yellow line reflects the dihedral plane, okay, and red line which reflects the C2. Now, this is the square planar molecule where this is a square planar molecule, right? So in this square planar molecule, if we can pass this line, okay, imaginary line passing through the center of that molecule, and if we can rotate at 180-degree rotations, so this fluorine comes over here and this fluorine comes over here, and we are getting the equivalent structure. So this is called C2. Okay, after 180-degree rotations, of this imaginary axis, what will happen? This fluorine comes over here and this fluorine comes over here. So this is called C2. Okay. Same way, another C2. This is C2. And if we can rotate at around 180-degree rotations, what will happen? This fluorine comes over here and this fluorine comes over here. Both these fluorine interchange their positions. So this is also C2. The dotted line which also reflects the C2. If we can rotate this dotted line, okay, so this fluorine comes over here, this fluorine comes over here. After 180-degree rotations, we are getting the equivalent structure. So third C2, this is fourth C2. Okay, so actually in square planar molecule, there are 4 C2s are present. Okay, and where is my principal axis? The principal axis, it is passing through the center. If I can rotate at around 90-degree rotations, so what will happen? This fluorine comes over here, this fluorine comes over here, this fluorine comes over here, and this fluorine comes over here. So this is an equivalent structure. So C4, this C4, if we consider as a principal axis, and this 4C2 are the subsidiary axis. These are the 4 subsidiary axes. 1, 2, 3, and 4. 4 C2s are there. Now, dihedral plane, what is the condition of dihedral plane? It passing through the center of that molecule. Now you can imagine this imaginary axis, dotted line, if we can consider as a sigma d. So it passing through the center of that molecule and divides the molecule into two parts, both the parts which are mirror images of each other. Both the parts which are mirror images of each other. Okay. So if we can imagine this dotted line passing through the center of that molecule, which divides the molecule into two parts. So this part, which is the mirror images of this part. Okay. The one condition is satisfied. Now, second conditions, it passing through the center of two subsidiary C2. Now look at this. This is the first C2. This is the second C2. So it passing through the angle between the two subsidiary C2. So this is called sigma d. तो इसको हम कहेंगे sigma d. So there is a one sigma d. Same way, this is also another sigma d passing through the center of that molecule and divides the molecule into two parts, one part and second part. Both the parts which are mirror images of each other, and it passing through the angle between the two subsidiary C2. So this is called second C2. So how many sigma d planes are there? There are two sigma d planes are present. यहाँ पे देखो, look at this. Look at this plane. This plane passing through the center of that molecule. Okay, and this is my one C2. This is my second C2. So it passing through the angle between the two subsidiary axes. So this is called sigma d. So all of you might be having cleared this doubt. What is a sigma d? Sigma d is nothing but the condition for sigma d is it is passing through the center of that molecule and divides into two parts. And second conditions for sigma d is it passing through the angle between two subsidiary C2. Okay, so it passing through the angle between two subsidiary C2, that is called sigma d. Okay. Now the last one, that is rotation reflection axis. So there are 5 symmetry elements we have discussed one by one. That is axis of symmetry, then followed by identity, then center of symmetry, mirror plane, and the last one, that is called rotation reflection axis, or which is also referred as improper rotations. Now rotation reflection axis, look at this methane molecule CH4. It has cubic symmetry. Now carbon, which is situated at the center, and the 4 hydrogens, they are situated at the 4 alternate corners. If hydrogen 1 is situated here, hydrogen 2, which is situated here, hydrogen 3 here, and hydrogen 4. So rotation about 360 by n axis followed by reflection through a plane. So these operations that would involve 2 operations simultaneously: rotation by n axis followed by reflection through a mirror plane. Okay, so if we assume that this is an imaginary axis, if we can pass this imaginary axis around which if I can rotate, okay, if I can rotate 90 degree rotations, अब इसको हम 90 degree पे rotate कराएंगे, so what will happen after 90 degree rotations? H1 comes over here, H2 comes over here, H3 यहाँ पे आएगा, and H4 यहाँ पे जाएगा. So after 90 degree rotations on Z axis, we are getting new structure. Now this new structure where H1 here, H2 here, H3 here, and H4 here. Now this is the original structure. Now compare with the original structure. Whether it is an equivalent structure? No. We can say that it is not an equivalent structure because H1 is here. Now the position of H1, यहाँ पे कोई atom नहीं है previously in the original structure. So therefore this is not an equivalent structure. Okay. Now second operations followed by reflection through a mirror plane, which is perpendicular to that rotation axis. So it would involve the 2 operations simultaneously: rotation by n axis, followed by reflection through a mirror plane, which is perpendicular to that rotation axis. So this plane, which is perpendicular to that rotation axis. So if we can put a plane over here, what will happen? The hydrogen is here, उसकी mirror image कहाँ पे मिलेगी? यहाँ पे. H3 is here, इसकी mirror image कहाँ मिलेगी? यहाँ पे. Okay, so H1 यहाँ पे है, तो इसकी mirror image यहाँ पे मिलेगी, and H4 यहाँ पे. Because when we are putting a mirror plane, तो उसकी इमेज कहाँ पे मिलेगी? तो H2 की यहाँ पे, H3 की यहाँ पे, H1 की यहाँ पे and H4 की यहाँ पे. So after performing that second operations by putting a mirror plane which is perpendicular to that rotation axis, and we are getting the new positions of all these four hydrogens, H1, H2, H3, H4. Now you compare with the original structure. Now you compare both this structure. Now both this structure, they are called equivalent structure. So after performing two operations, rotation by an axis followed by reflection through a plane, and we are getting the new structure, this structure which is equivalent to the original structure. So therefore we can say that this methane molecule which has improper rotations, that is called a rotation reflection axis is present. So these operations को हम क्या कहेंगे? C4, we have performed first C4 followed by sigma H. So therefore this operation is called S4. Okay. So this is called rotation reflection axis. Now, point group. Now, how to define point group of a particular molecule? Now, point group, we can say that it is a shorthand notation. So, point group is a shorthand notations which gives an information about the number of symmetry operations which are possible in a molecule. Okay. So, point group is nothing but the summation of all the symmetry operations which are present in that particular molecule. Okay. So point group is called set of symmetry operations. So point group is called a set of symmetry operations. So for example, water molecule. So in water molecule, how many total number of symmetry operations are present? So we can say that C2 is present and 2 sigma V planes are also present. Okay, identity is present. So then we can say that C2 plus E plus C2, that is called C2. Now C2 plus 2 sigma V planes are also present. Therefore, we can say that C2V. So which is symbolized by C2V. So that point group is called C2V. Okay. Now look at this, some of the example. Now look at this three-dimensional structure of this molecule, CHFClBr. Okay. Now this circle which indicates that carbon. If we assume this is carbon, if I can consider as a hydrogen, this is fluorine, and this is bromine. Now, which symmetry elements are present in that molecule? This is asymmetrical molecule because all the corners where there are different atoms are there. Hydrogen, chlorine, bromine, okay, chlorine. So here no symmetry elements are present. Okay. If I can pass imaginary line. Now, if I can rotate after performing cyclic operations, what will happen? These atoms comes over here, these atoms comes over here, and these atoms comes over here. But here, these atoms comes over here. Sorry. So, but here, all these atoms, they are different atoms. So we can say that this is not an equivalent structure. Therefore, rotation axis is absent. Okay. Center of symmetry I is also absent. Because if I can start my journey from this point to the center, on the other side of the center, यहाँ पे ये atom present नहीं है. If I can start my journey from this point to the center, on the other side of center, there is no any atom. Therefore, center of symmetry I is also absent. Okay, mirror plane which is also absent. We are not getting the mirror image. If we can put mirror plane over here, we are not getting the mirror image. Therefore, mirror plane is also absent. So only one operations is present, that is called identity. So every molecule, they are of having their own identity. So identity is always present in every molecule or compounds. Okay. So when only identity is present or only one rotation axis is present, so that is if I can perform 360-degree rotations. So after 360-degree rotations, what will happen? The atoms, they are at the same positions after performing of these cyclic operations. Okay. So only one identity E is present. So therefore, the point group of that molecule is C1. Now, second molecule. Now look at the second molecule. Starting with, if we can start with any rotation axis is present, we can check. If we can pass imaginary line through this molecule, and if we can rotate, तो हमें equivalent structure form होगा नहीं. Okay, so this is x-axis. If I can consider as an imaginary axis, and if I can rotate at around 180-degree rotations, so these two hydrogen interchange their positions. But here on the other side, where chlorine is present and here bromine is present, so we are not getting the equivalent structure. So this imaginary axis is absent. This second on z-axis, if I can rotate at around 180-degree rotations, what will happen? We are getting the equivalent structure? No. So therefore, rotation axis is absent. Okay. Is there any mirror plane is present? Is there any mirror plane? Yes. So there is one mirror plane is present. This is the planar molecule. And if we can pass this plane in such a way that it divides the atoms into two parts, both the parts which are mirror images of each other. So this is called only mirror plane sigma. So this sigma is present. The rest of the symmetry operations are absent. Only sigma is present and identity E is present. So in this molecule, there are two symmetry elements are present. Which one? Identity E and sigma. Therefore, the point group of this molecule E plus sigma, that is called CS. So E is also called as C1. इसलिए यहाँ पे so C1 plus S is equal to CS. Now here in this molecule, where only one symmetry operations, that is I is present. Look at this. If I can start my journey from this bromine atom to the center, on the other side of the center, if I can get the same atom, that is bromine, I is present. If I can start my journey from this hydrogen to the centers, on the other side of center, we get the same hydrogen. Therefore, center of symmetry I is present. If I can start my journey through the center, and on the other side of center, if I can get the same atom, that is chlorine. So I is present. So in this molecule, the rest of the symmetry elements are absent. Rest of the symmetry elements are absent. Only identity E and center of symmetry I is present. Therefore, the point group is Ci. Now look at this linear molecule, HCl. Now both the end having different atoms, hydrogen and chlorine. Okay, but it is a linear molecule. Now this linear molecule have if we can pass an imaginary axis passing through the center of that molecule, okay, which is situated on the x-axis. Now if we can rotate at any degree, if we can rotate at 1 degree, we are getting the equivalent structure. If we can rotate 5 degree, we are getting the equivalent structure. If we can rotate at around 45 degree, we are getting the same structure, equivalent structure. Okay, if we are rotating at 90 degree, so at any degree of rotations, we are getting the equivalent structure. Therefore, this axis is considered as C infinite. Okay, so when we are talking about the linear molecule always have infinite axis. Okay, so this is the C infinite. Okay, C infinite. Simultaneously, which of the other symmetry elements are present? Now, the second one, that is mirror plane. So if we can pass a mirror plane in such a way that which is parallel to the rotation axis, and it divides the molecule into two parts. So this is called sigma v. So one sigma v, okay, at any angle. If you can pass a plane at any angle, we are getting the same or equivalent structure. Therefore, infinite number of sigma v planes are also present. So, and the rest of the symmetry elements are absent. Center of symmetry I is absent. If I can start my journey from this hydrogen atom through the centers, on the other side of centers, we are not getting the same atom. Therefore, center of symmetry I is absent. Same way, other symmetry elements, sigma h is also absent. Sigma h kahan pe aayega? This is sigma h. Okay. So if I can pass sigma h, and this is the rotation axis, which is perpendicular to that rotation axis, but we are not getting the mirror image. यहाँ पे hydrogen है, यहाँ पे chlorine है. So we are not getting the mirror image. Therefore, sigma h is absent, right? So only which of the symmetry elements are present? Which of the symmetry elements are present? That is E is present. E is present plus C infinite. Okay, C infinite is present and plus sigma V is present. It is very difficult for me to write this sentence. So यहाँ पे कौन-कौन से symmetry elements are present? E is present, identity E is present, plus C infinite is present, which is on the x-axis, and infinite number of sigma V planes are also present. So the point group is E plus C infinite, that is called C infinite. Now C infinite plus infinite number of sigma V planes are present. Therefore, the point group is C infinite V. So look at this. This is C infinite V. Now, when the molecule is linear and the both the end having same atoms, okay, both the end having same atom, like carbon dioxide. Carbon dioxide is a linear molecule. The center part, which is situated by the carbon, and the two end, which is occupied by the two oxygen. So it is a linear molecule, both the ends having same atoms. And in this linear molecule, what is the point group? Here, D infinite X. Why it is not C infinite V? But because here, both the end having oxygen atoms. Now, where is my rotation axis? So if we can pass this axis through the center of that molecule, and if we can rotate at any degree, 1 degree, 5 degree, 10 degree, 15 degree, at any particular degree of rotations, we are getting the equivalent structure. Therefore, it is called as C infinite. Okay. Now, not only one rotation axis are present. Now, other C2s are also present. Now, look at this second. Now, if I can rotate this axis at around 180 degree rotations, so what will happen? So this oxygen comes over here and this oxygen comes over here. So this is my C2 and this is my third C2. Okay, if I can rotate and if I can pass the imaginary axis through the center of the molecule on the y-axis, and if I can rotate it, so what will happen? This oxygen comes over here and this oxygen comes over here. So third C2 is present. So C infinite is present plus two C2s are also present. So when C infinite is present along with two C2s are present, then the point group is C infinite plus 2C2. Therefore, it is called D infinite. So all of you just keep in mind that because the principal axis is C infinite. So therefore, it has a number of symmetry elements are present. So therefore, C infinite plus these 2C2, that is called D infinite. Followed by, as we have discussed earlier, this is the one sigma V. Okay, at any particular angle, if we can put on the x-axis, we are getting the mirror image, and which is parallel to the C infinite. Therefore, this is called sigma V. Okay, so this sigma V, there are a number of sigma V planes are present on the x-axis. Therefore, infinite number of sigma V planes are also present. So sigma h is also present. Look at this. यहाँ पे sigma h is also present. If I can put the sigma h over here and which is perpendicular to this principal axis, so this is called sigma h. Okay. So one sigma h is also present. So what is the point group of this molecule? The point group of this molecule is E plus C infinite. The E is equal to C infinite. Now C infinite plus infinite number of plus 2C2, that is called C infinite plus 2C2, that is called D2, D infinite, sorry. Now D infinite plus infinite number of sigma V and sigma H, the point group is D infinite H. Now, these are some of the examples where higher symmetry elements are present, number of symmetry elements are present. So tetrahedral molecule. So in tetrahedral molecule where a number of symmetry elements are present. Okay. So they are specific molecule, they are having higher symmetry and therefore they are having specific name tetrahedral, octahedral and icosahedral. Now icosahedral, there are total of how many individual operations are there? Total number of 120 individual operations are there. Therefore, they are giving polyhedral molecule like tetrahedral, octahedral, and icosahedral. So the term symbol or point group of this molecule tetrahedral TD, for this molecule octahedral, and this is called icosahedral. Now look at this. How to define the point group? Point group कैसे find out करते हैं? For example, this is a molecule. Now, if this molecule is linear, okay, so if the molecule is linear and it has a center of symmetry I is present, yes, okay, so this is a molecule which has a linear structure. If it has a center of symmetry I is present, so what is the point group of that molecule? The point group of that molecule is D infinite H. So all of you just keep in mind that if the molecule is linear, center of symmetry I is present, then the point group is D infinite H. If molecule is linear, but center of symmetry I is absent, then the point group is C infinite V. C infinite V. So जैसे कि हमने previously discuss किया था, these are the two examples. This is the linear molecule where center of symmetry I is absent because this end having hydrogen and this end having chlorine. So यहाँ पे center of symmetry I is absent. So if center of symmetry I is absent, then the molecule is having C infinite V symmetry. So this is having C infinite V symmetry, point group. However, if center of symmetry I is present, then the molecule having D infinite H point group. This molecule. So carbon dioxide is a linear. Here center of symmetry I is present. If I can start my journey from this oxygen atom through the center, this is the center of that molecule. On the other side of a center at the same distance, if I can find the same atom like oxygen, so center of symmetry I is present. So यहाँ पे center of symmetry I is present. So center of symmetry I is present. Therefore, the point group is D infinite H. Okay. So this is about the linear molecule. Linear molecule में if center of symmetry I is present, then D infinite H. If linear molecule having center of symmetry I is absent, then the point group is C infinite V. On the other side of the molecule, if the molecule is not linear, and it has two or more rotation axis, where the value of n is greater than 2. Okay, so where the value of n stands for number 4. So more than value of n is equal to more than 2. So like C3, C4 like that. Okay, so in that case, and center of symmetry I is present. So along with if C5 rotation axis is also present, then the point group is icosahedral. So icosahedral molecule, molecule having icosahedral point group where 120 different operations are present. Okay, so how to find out the icosahedral point group? So here the molecule which is not linear and no, okay, but it has a number of rotation axis where the value of n is greater than 2. Okay, yes. Center of symmetry I is present, yes. Also with having number of C5 axes are also present, then the point group is icosahedral. Now C5 axis is absent. No. Okay. So in that case, the point group is octahedral. Now here, more than two or more number of rotation axes are present. Here, center of symmetry I is absent. In that case, the molecule is tetrahedral. So here, look at this. These are the three examples where icosahedral, where C5 axis is present. Okay, 6 C5 axes are present. C5 axis is present. Center of symmetry I is also present. So here, center of symmetry I is also present. So this is a icosahedral point group molecule where center of symmetry I is present. So therefore, it has icosahedral. Octahedral, C5 is absent. Here, C5 axis is absent, and hence C5 axis is absent. Therefore, octahedral point group. Center of symmetry I is absent, then it is tetrahedral. So look at this. यहाँ पे center of symmetry I is absent, therefore it has a tetrahedral molecule. Now, if the molecule having a number of rotation axes, but the value of n is equal to 2, n is equal to 2, number of C2s are present, but it is not more than 3, 4 like that. So if number of C2s are present, yes, which are perpendicular to that principal axis, yes, it has a sigma h is also present, then the point group is DNH. Okay, so in that case, the molecule have point group DNH. Now, if the sigma h is absent in that molecule, but number of sigma d planes are present, so the point group is DNP. The point group is DNP. Now, if sigma d planes are also absent, so in that case, the point group is DN. On the other side, number of subsidiary axes are absent. Only rotation axis is present, but sigma h is present. In that case, the point group is CNH. But sigma h is absent and number of sigma v planes are present. Okay, in that case, the point group is C and V. Okay. However, if sigma v planes are also absent and S2 planes are present, so in that case, the point group is S2N. And if S2N is also improper rotation is also absent, so in that case, it is having CN point group. Now on this here, number of C2 axes are absent. Okay, rotation axes are absent. Here only sigma h is present. Okay, then the point group is CS. And if the sigma h is absent, only center of symmetry I is present, then the point group is CI. And if I is absent, only identity is present, then the point group is C1. So in this way, we can differentiate the number of point groups in a molecule. So I will stop my presentation here. Okay, in this session, so I'm going to discuss about the group theory. Previously, we have discussed about how to find out the point group of a molecule. Now, in group theory, it was first developed by E. Galois in 1811 to 1832. A group theory, it is a branch of mathematics which is applied to any set of elements obey the necessary conditions to be called a group. Okay, so in a point group, there are a number of symmetry elements are present. The point group is nothing but a summation of all the symmetry elements. Okay, so any set of symmetry elements, they must obey the necessary conditions to be called a group. Now, chemists use a subset of group theory that is called as representation theory. So we are dealing with the representation theory. Now look at this. Now symmetry operations and matrices. How the symmetry operations change the Cartesian coordinates. Change the Cartesian coordinates of the molecules. Okay. So look at this water molecule. Water has band structure. This is oxygen, which is at the center, situated at the center, and these are the two hydrogens. Okay. Now these are the three Cartesian coordinates x, y, and z. Okay. Now if I can perform any operations on the water molecule, for example, C2 operations, which is situated on the z-axis. Now, which is situated on the z-axis. This is the imaginary line passing through the center of the molecule, and if I can rotate it at around 180-degree rotations, after 180-degree rotations, H2 and H3 interchange their positions. Okay. So previously we have discussed about the position of H2 and H3. Now here, what we have to observe. So on performing any operations like E operations, C2 operations, sigma xj and sigma yj operations, what we are getting? These are the three Cartesian coordinates. So what is the effect of combining two or more symmetry operations if performing them one after another? Okay. So when we are performing that symmetry operations, what should be the change is observed in x, y, and z. Okay, Cartesian coordinates of a molecule. So effect of operations on the coordinates of H2. Now, for example, if I can perform E operations. So if I can perform E operations, what should be the positions of x, y, and z after performing E operations? So these are the three Cartesian coordinates x, y, z. Now, if I can perform E operations. Now, E operations, then after what is my final results? The final Cartesian coordinates, it becomes x, y becomes y, and z becomes z. So why we are getting the same results? Because we have performed E operations. So what is the condition of E? The E operation is no change is made in the molecule. The molecule will remain as it is. So therefore, after performing E operations on water molecule, so the position of x becomes x, z becomes z, and y becomes y. So therefore, the Cartesian coordinates x, y, z after performing E operations, they remain as it is. Therefore, the value becomes x, y, and z. Now, instead of E, if we can perform C2 operations. Now, where is my C2 on water molecule? This is my C2. Okay. This is C2. Okay. Now, if I can perform C2 operations, so after C2 operations, what is the position of x, y, and z after performing C2 operations? So if I can perform C2 operations, so x becomes क्या होगा? X becomes minus x. Y becomes minus y, and z becomes plus z. Because C2 is situated on the z-axis, the position of z will remain as it is. So here, after performing C2 operations, x becomes minus x, ऐसे होगा. Y becomes minus y, but z becomes as it is. So x becomes minus x, y becomes minus y, and z becomes plus z. What about sigma v x z? Okay, now look at this. Here, this is my C2. Okay, and this is oxygen. This is two hydrogen, and these are the two planes, two mirror planes, which is present in water molecule. One which is called sigma v y z, and another one which is called as sigma v x z. So why it is called sigma v x z? Because x and z axis, they are situated into the plane. So x and z, they are situated into the plane. Therefore, this plane is called sigma v x z. And why it is called sigma v y z? Because y and z, they are situated into the plane. Therefore, this plane is called sigma v y z. So if I can put sigma v y z in such a way that which is parallel to the rotation axis, so this plane is called sigma v y z, vertical plane. And this plane is also, if I can put the plane in such a way that it divides the molecule into two parts, and both the parts which are mirror images of each other. So how many sigma v planes are present? Two planes, sigma v x z and sigma v y z. Now if I can perform sigma v x z, so this plane, I am talking about this plane. If I can perform sigma v x z, so what is the position of x, y, and z after performing sigma v x z? So x and z, they are situated into the plane. Therefore, the position of x and z remain as it is. However, y, which is perpendicular to this plane, so uski image kahan pe mila? This is a mirror image. So therefore, y becomes minus y. So after putting a plane sigma v x z, so y becomes minus y. So therefore, the final coordinates x become x, y becomes minus y, and z becomes plus z. Same way, if I can put the sigma v yz plane, so this is the sigma v yz plane. If I can put sigma v yz plane, what is the position of Cartesian coordinates x, y, and z after performing these operations? So if I can put sigma v yz plane, so y and z Cartesian coordinates, they are situated into the plane. So therefore, their positions remain as it is. So y and z, they will remain as it is. However, x which is perpendicular to that plane, therefore उसकी mirror image कहाँ पे मिलेगी? On the back side. So x becomes minus x. So therefore, after putting sigma v yz plane on the molecule where only x is changed, however y and z, they remain as it is. Okay. Now, same way, the combination of two operations. So if I can perform two operations simultaneously, C2 operations followed by sigma v xz. So what is my final answer? So for example, these are the x, y, z Cartesian coordinates x, y, and z. Okay. Now if I can perform C2, now where is my C2? This is C2. Okay. If I can rotate C2, so after 180 degree rotations, what will happen? The x becomes minus x, y becomes minus y. But z is situated into the C2. Therefore, the position of z will remain as it is. So look at this, x becomes minus x, y becomes minus y, and z becomes plus z. Followed by the second operations. So after we are getting minus x, minus y, and z on the same molecule, and if we can put the sigma v xz plane. So now if we can put the sigma v xz plane, this is my sigma v xz plane. This is my sigma v xz plane, and this is minus x. Okay, on the same operations, if we can perform the second operation sigma v xz, so what the position of minus x becomes minus x, but minus y, which is perpendicular to the sigma v xz, therefore it becomes plus y. So minus y, it becomes plus y, and z remain as it is. So therefore, after performing two operations, one after another, first we perform C2 operations followed by sigma v xz. What is my final answer? The final coordinates are minus x, y, and z. Now these are the coordinates of sigma v yz. So my answer is C2 into sigma v xz. What is my answer? My answer is sigma v yz. Now matrix. Okay. So these symmetry elements, E elements, sigma v xz, sigma v yz, C2 elements, how to represent these elements in terms of matrix. Okay. So now we shall discuss about the matrix. So matrix is an array of numbers arranged in rows and columns. Okay. So these are the rows, and these are the number of rows, and these are the columns. So matrix is an array of numbers arranged in rows and columns. Okay. So now this matrix, for example, where 1, 2, 3, 4, 5, 6. So 6 rows and 6 columns. These are the 6 columns. So 6 into 6 dimensional matrix. Now, what are the diagonal elements? Now, this is a bulky matrix or large matrix where top left corner to the right bottom corner. So along this line, this is called diagonal lines. And the elements situated along the diagonal lines, these are called diagonal elements. So here in this matrix A11, A22, A33 up to AMN, these elements are called diagonal elements. So from top left corner to the bottom right corner, that line along the line, that is called diagonal line, and the elements are called diagonal elements. Now look at this. Now transpose of a matrix. So what do you mean by transpose of a matrix? Now transpose of a matrix is obtained by replacing every element Aij with element Aj. So that means this is a matrix, okay, and this is my row 1, 4, 6, 2, 7, 8, and 9, 3, 5. These are the rows. And what is the values in columns? 1, 2, 9, 4, 7, 3, and 6, 8, 5. These are the column value. So after performing transpose of a matrix, so row is converted into matrix column, and column is converted into row. So look at this, 146, 278 and 935. So now they becomes column. So 146, 278 and 935. Okay. So the transpose of matrix is given by A transpose is equal to 129, 129. So column is converted into row. 473, this is a row. 685, this is a row. Okay. So column is converted into row or row is converted into column. So transpose of a matrix is obtained by replacing every row element into column. Okay. Okay. Now E matrix. Now we derive the symmetry elements in terms of matrix. So how to derive the E matrix? So what is the value of E matrix? Now consider the transformation of a general point. So if we can imagine the point with their respective coordinates are x1, y1 and z1. Okay. So if we consider an imaginary point with their respective coordinates are x1, y1 and z1. Now if we perform E operations. Now if I perform E operations, so E operation, that means no change is made in the molecule. That means if I can perform E operations, after E operations, if we assume that we are getting the new coordinates x2, y2 and z2. So final after operations. So if I can perform E operations, these are my initial coordinates, initial before operations. So x1, y1, z1, these are the coordinates. After performing E operations, any operation, E operations, and we are getting the final coordinates, that is x2, y2 and z2. But we know that E operations, that means no change is made in the molecule, leave it alone operations. So the final coordinates are equal to the initial coordinates because E operations में no change is made in the molecule. कोई भी change नहीं होगा. So that therefore initial coordinates is equal to final coordinates. So x2 is equal to x1, y2 is equal to y1, and z2 is equal to z1. So after performing E operations, x2 becomes x1, y2 becomes y1, and z2 becomes z1. So these are my final coordinates x2, y2, and z2. If we can represent in terms of three-dimensionally, so on x-axis the value is 1 because x, so 1 x1, but on y-axis it is 0, on z-axis it is also 0. So 1 x1 plus 0 y1 plus 0 z1. Same way for y2. y2 on x-axis it becomes 0, so 0 x1 plus 1 y1 plus on y-axis it is value 1 and z-axis it is 0. So 0 x1 plus 1 y1 plus 0 z1. On z-axis it is equal to 0 x1 plus 0 y1, but on z-axis it becomes 1. So x2, y2, z2 in terms of matrix. So we are getting the new matrix 1, 0, 0. The values 0, 1, 0 and 0, 0, 1. So 1, 0, 0, 0, 1, 0 and 0, 0, 1, x1, y1 and z1. So the final E matrix. So what is the value of E matrix? The matrix E matrix value is 1, 0, 0, 0, 1, 0 and 0, 0, 1. Same way, sigma matrix. Now, what is the value of sigma matrix? Now, to work out a matrix for reflection plane, it is considered to lie along with one of the principal Cartesian planes, xy, xz, and yz. Okay, so planes are designated as sigma xy, sigma y, xz, and sigma yz. So these are the initial coordinates before operations x1, y1, and z1. If I perform sigma reflection operations, so what my final coordinates are x2, y2, and z2. So these are my final coordinates after performing sigma reflection operation. Now note down the changes from for reflection in sigma sigma xy plane. So if I consider among these three xy, xz, and yz. So if I can consider sigma xy plane. So what is my final coordinates? So x2 becomes x1, y2 becomes y1, but z2 is equal to minus z1 because this plane which is situated in xy. So x and y coordinates, they are situated into the plane. However, z, which is perpendicular to that planes, so therefore their final coordinates z2 is equal to minus z1. So therefore x2, y2, z2. So 1 x1 plus 0 y1 plus 0 z1. Same way, y2 is equal to 0 x1 plus 1 y1 in plus 0 z1. However, z2 is equal to minus z1. So z2 is equal to 0 x1 plus 0 y1 minus z1. So therefore 1 0 0 0 1 0 0 0 minus 1. So sigma xy matrix, the sigma xy matrix value is equal to 1 0 0 0 1 0 0 0 minus 1. what is the value of what is the value of sigma v sigma x z? So in that case, x and z coordinates, they are situated into the plane. However, y, which is perpendicular to the planes, so in that case, sigma x z 1 0 0 0 minus 1 0 0 0 1. Okay, and what about the sigma v x z or y z? What are the metrics for sigma y z? So in that case, y and z coordinates, they are situated into the plane. However, x, which is perpendicular to the planes, so therefore x value is minus 1. So minus 1 0 0 0 1 0 0 0 1. Look at this. So these are the metrics for sigma v y z, and this is sigma v x z. Same way we can get the matrix for I matrix. So I operations, while performing I operations, so in that case I operations x1 y1 z1 I operations, it becomes x2 y2 and z2. So for I operations where x2 is equal to minus x1, y2 is equal to minus y1, and z2 is equal to plus z1. So all of you just keep in mind that I matrix, for the I matrix, their value is minus 1 0 0 0 minus 1 0 0 0. Now this is important. How to derive a matrix for rotation axis? Now CN matrix. Suppose we have to derive the CN matrix. CN matrix, cyclic rotations that should be in anti-clockwise directions or clockwise directions. So rotations that should be performed in anti-clockwise directions and clockwise directions. So first we derive the matrix for in anti-clockwise rotations. Now look at this. Look at this. Let CN axis be the collinear with the Z axis. So this is Y axis and this is X axis, red line, which indicates that this is X axis, this is Y axis, and Z, which is out of plane. Now C2 axis, which is situated on the Z axis. So CN axis be collinear with the Z axis. Okay, so CN, which is collinear with the Z axis. This is Z axis. Sorry. This is Z axis. Okay, out of the plane. So CN axis be collinear with the Z axis and designated as CNZ. Now in a Cartesian space, in a Cartesian space where point P1 with its initial coordinates x1, y1, and z1. Okay, so this is the point P1 with its initial coordinates x1, y1, and z1. Now if I perform rotation axis on Z axis, so this is the Z axis and rotation on Z axis, C2 rotations. So after C2 rotations at theta degree, I am getting a new point P2. So P1 changes to point P2 with its new coordinates x2, y2, and z2. Okay. Now point P1 joining the line with origin, that is called vector R. Okay. So a line joining the point P1 and the origin, that is called vector R. So this is vector R. Okay. When rotation is carried out, so when rotation in anti-clockwise, so यहाँ से हम rotation करेंगे. Rotation is carried out on the Z axis, and we are getting the new point P2 with its final coordinates x2, y2, and z2. हमने कितना rotation किया? We have performed rotation on Z axis theta degree. So this is theta degree rotations. Okay, and with its final coordinates x2, y2, and z2. So look at this. The point P1 with its initial coordinates x1, y1, z1. So after performing rotation theta degree in an anti-clockwise manner, this is anti-clockwise rotation, and we are getting the new point P2 with its final coordinates x2, y2, and z2. Now here, rotation is performed on z-axis. So rotation is performed on the z-axis. So therefore, since the rotation is around on z-axis, therefore the coordinates z2 is equal to z1. Let me know that because we have performed the cyclic operations on z-axis. So therefore their coordinates z2 is equal to z1. Now we have to find out x1, y1. Okay. So what is the value? For changes in x1 and y1, consider the two triangles. So these are my two triangles. This is triangle 1. Okay. And this is triangle 2. So we have to consider these two triangles, first triangle and this is second triangle. This is second triangle and this is first triangle. So consider these two triangles. Okay. Now, first you have to concentrate on first triangle. What is the value of sine theta? What is the value of sine theta? The sine theta is equal to y1 upon r. Okay. So consider the value. What is the value of sine phi? Sorry, sine phi. This is the angle between x-axis. That is phi, arbitrary angle, and this is the true angle. That is theta. So while we consider the first triangle, and what is the value of sine phi? The sine phi is equal to y1 upon r. Look at this. Sine phi is equal to y1 upon r. And same way, therefore y1 is equal to r sine phi. This is equation number 1. Now what is the value of cos phi? So what is the value of cos phi? So cos phi is equal to x1 upon r. You have to concentrate on first triangle. Right now I am discussing about the first triangle. So sine phi is equal to y1 upon r and cos phi is equal to x1 upon r. This is simple trigonometry relations. So right now we are discussing about simple trigonometry relations. So as per the simple trigonometry relations, sine phi is equal to y1 upon r and cos phi is equal to x1 upon r. Look at this. Cos phi is equal to x1 upon r. So x1 is equal to r cos phi. This is equation number 2. Now here theta is the specified angles. This is the specified angle of rotation, whereas phi is an arbitrary angle. So what is phi? Phi is an arbitrary angle. Now we consider sine phi. Now we consider the second triangle. So look at this second triangle. This is second triangle. Now while second triangle where sine theta plus phi, y2 upon r and cos theta plus phi, that is x2 upon r. Okay. So what is the value of sine theta plus phi? So sine theta plus phi is equal to y2 upon r and cos theta plus phi, that is x2 upon r. Look at this. So sine theta plus phi is equal to y2 upon r and cos theta plus phi is equal to x2 upon r. So therefore y2 in terms of y2, that is r sine theta plus phi and x2 is equal to r cos theta plus phi. This is equation number 4. Now rearranging equation 3 and 4 using simple trigonometry relations, and we are getting x2. So x2 is equal to r cos theta. When we relieve this bracket, so r cos theta cos phi minus sin theta sin phi. Okay. So x2 is equal to r cos theta cos phi minus r sin theta sin phi. This is equation number 5. And for y2, using simple trigonometry relations, when we relieve this bracket, so r sin theta cos phi plus cos theta sin phi. Okay. And therefore y2 is equal to r sin theta cos phi plus cos theta sin phi. This is equation number 6. One minute. Now substituting the value of r cos phi and r sin phi from equation number 2 and 1 into equation number 5 and 6 respectively, we are getting, while we insert the value of r cos phi and r sin phi in equation number 5 and 6, we are getting the simplified value, that is x2 is equal to x1 cos phi minus y1 sin phi, and y2 is equal to x1 sin phi plus y1 cos phi. This is equation number 7 and 8. Now on expanding the equations for x2, y2 and z2, so in terms of this equation, three-dimensionally, so what is the value? x2 is equal to x1 cos theta minus y1 sin theta plus 0 z1. Okay. For y2, three-dimensionally, x1 sin theta plus y1 cos theta plus 0 z1. And same way, z2 is equal to 0 x1 plus 0 y1 plus 1 z1, because z2 is equal to z1. Okay. So x2, y2 and z2, finally we have derived the matrix cos theta minus sin theta 0, sin theta plus cos theta 0, 0, 0, 1. Look at this final matrix. So final C and Z matrix in an anti-clockwise rotations. What is the value of C and Z matrix? That is cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Same way, get the matrix corresponding to the clockwise rotations by simply replacing theta into minus theta. Okay. While we are talking about the clockwise rotations, previously we have derived a C and Z matrix in an anti-clockwise rotations. For clockwise rotations, what will be the change in that matrix? So instead of theta, you put only minus. Okay. So theta into minus theta. So that we are getting the matrix for clockwise rotations. So C and Z. Previously, we have derived a matrix Cn that is cos theta, sin theta 0, sin theta, cos theta 0, 0, 0, 1. Now, in a clockwise rotations, where instead of theta, you put minus theta, minus theta, minus theta. Okay. So C and Z matrix cos theta, sin theta 0, minus sin theta, cos theta 0, 0, 0, 1. So similarly, it is possible to work out what the matrices for Cnx and Cny. So this is the matrix of Cnx. So 1, 0, 0, 0 cos theta sin theta 0 minus sin theta cos theta. Okay. And same way Cny. This is the matrix for Cny matrix. So for example, depending on the value of theta in the CNZ matrix, suppose the value of theta is equal to 0 or 360. So inside the value of theta is equal to 360. So cos 360 is equal to 1 and sin 360 is equal to 0. Look at this. Sin 360 is equal to 0, cos 360 is equal to 1. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is E matrix. Now C and Z, if theta is equal to 180, if we consider theta is equal to 180 degree, so insert the value of theta is equal to 180. So look at this, cos 180 is equal to minus 1. So cos 180 minus 1, sin 180 0, 0, sin 180 0, cos 80 180 minus 1 0, 0, 0, 1. Okay, so C and Z matrix for theta is equal to 180 degree. So this is the matrix. Theta is equal to 120. This is my matrix. C4 matrix, that means theta is equal to 90 degree. So what is my matrix? In this way, we can derive the matrix for cyclic operations. Now, lastly, matrix for sigma plane of symmetry. So how to derive the matrix for plane of symmetry or mirror plane? Now, assume that this is my point P1 with its initial coordinates x1 and y1. Okay, and the line joined to origin that is called vector r. Okay, so it is my initial point with initial coordinates x1 and y1. If we can put the plane or mirror plane in such a way that which is, if we put a matrix or if we put a plane which makes an angle with the x-axis, that is B. Okay, so this is this line which reflects the mirror plane. Okay, आपको ऐसे रखना है. So the angle with the x-axis, that is considered to be a B. Okay. Now suppose R is a vector and point P1 is a point on it. After reflection through the mirror plane, so if we can put the mirror plane, उसका reflection कहाँ पे मिलेगा? The point P1 changes to point P2. So इसका reflection मिलेगा यहाँ पे with its final coordinates x2 and y2. Now same way, using the simple trigonometry relations, what is the value of x1 upon r? So x1 upon r, that is cos theta plus b. Here cos theta plus b, therefore x1 is equal to r cos theta plus b. Same way, what is the value of y1 upon r? So y1 upon r is equal to sin theta plus b. So therefore y1 is equal to r sin theta plus b. This is the first triangle and this is second triangle. Now we focus on the second triangle. So what is the value of x2 upon r? So x2 upon r is equal to cos theta minus b. So this is angle cos theta minus b, and y2 upon r, that is sin theta minus b. But यहाँ पे क्या होगा? So x2 upon r, that is called theta minus b, or x2 is equal to r cos theta minus b. So x2 is equal to r cos. By putting theta minus b, we can write down in this way: theta plus b minus 2b. Values are same. So theta plus b minus 2b is equal to theta minus 2. So instead of theta minus b, we have write down in this way theta plus b minus 2b. Okay, so this is equation number 3. Now y2 upon r, why it becomes minus sine theta minus b? Because look at this here, in polar coordinates in the fourth quadrant where the value of cos is equal to plus, however the sign is minus, so that's why the value of sine is minus. So y2 is equal to minus r sine theta minus b. Okay, so y2 is equal to minus r sine, instead of theta minus b, we can write down in this way also theta plus b minus 2b. This is equation number 4. Now equation 3 and 4 by using simple trigonometry relations. So x2 is equal to r cos theta plus b, while we relieving this bracket cos theta plus b cos 2b plus minus minus plus sine theta plus b sine 2b. Okay, so therefore r cos theta plus b cos 2b plus r sine theta plus b into sine b. And x2 is equal to simplifications x1 cos 2b plus y1 sine 2b, because we have insert the value. So x1 is equal to r cos theta plus b from equation number 2 and 3. So based on that, we have insert the value. Therefore, x2 is equal to x1 cos 2b plus y1 sine 2b. Same way for y2 is equal to minus r, using simple trigonometry relations. Therefore, sine theta plus b cos 2b minus plus becomes minus. So minus cos theta plus b sine 2b. So is equal to minus r sine theta plus b cos 2b plus minus minus plus r cos theta plus b sine 2b. So after simplifications, where the value of y2 is equal to minus y1 cos 2b plus x1 sine 2b, and y2 is equal to x1 sine 2b minus y1 cos 2b. It is equation number 6. So the matrix x2 y2, it becomes here x1 cos 2b y1 sine 2b, okay, and x1 sine 2b minus y1 cos 2b. Okay, so this is the value, and therefore x1 cos 2b sine 2b minus cos 2b x1 y1. So this is two-dimensional way. So in three-dimensional, where the transformation matrix for the reflection through xz plane, so sigma xz, that was x1 y1 z1, that is cos 2b sine 2b 0, sine 2b minus cos 2b 0 0 0 1. So x1 y1 z1. And for the transformation matrix for reflection through xy plane, that is sigma xy, that is x1 y1 z1, cos 2b 0 sine 2b 0 1 0 sine 2b 0 minus cos 2b x1 y1 z1. So in this way we can derive the matrix for mirror plane. So this is mirror plane sigma v xz, and this is sigma xy. We are least concerned. We just skip this one. Okay, and we are discussing about the time is almost over. So I can dismiss the class because we have a very limited time. So in this stipulated time, we should cover the point group and the group theory, certain parts of the group theory. So I will stop my class over here. Thank you very much.